Alright, so in section 5.2 we're going to be talking about solving trigonometric functions. And I'd like to start by comparing two similar but distinctly very different problem types. So the first kind of problem should look familiar. If we're asking to find the exact value for sine inverse of 1/2, this looks like something that we would have done in the previous chapter, right? So how do we do a problem like finding the exact value of sine inverse of 1/2? Should still be able to do this. It's just like a week ago. What do we need to do a problem like this? Anyone? Pretty disappointing, I have to say, that amongst the 30 or so students here, not one person can remember a problem from a week ago on how to do something like this without having to flip back through the notes. That there were a dozen, we did like in 3 worksheets. Yeah, so you need to look at your unit circle. And what are we looking for on the unit circle? The y-coordinate equaling 1/2, okay. So if I go to my unit circle, and I look for where the y-coordinate is 1/2, I see 2 locations where that's true. Is that it? Nope. 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 One of these values is an impossible thing to get. Here's the range for sine inverse of 1/2. Yes, Allison? I can't hear what you said. It was too quiet. Yeah. So the range for sine inverse of 1/2 is negative pi over 2 to positive pi over 2. So that answer is not one that we would list. We would list just one solution to this. Why is this the case? That the range for this is negative pi over 2 to positive pi over 2. Because of how the graph is. Can you elaborate on that? What's it? The line only goes up a certain amount. Allison? No, I'm asking why the range is this for sine inverse. We chose it to be that. We did. Why did we choose that? What did we need sine inverse to be? We need it to be a function, right? Remember the graph of sine, looks like this, right? We just strictly switch the x's and y's, what we get is not a function, right? It's not programmable into a calculator. You can't do anything digital with it. That's a problem. How did we solve that problem? We just restricted the domain of our sine function so that it covered all the y coordinates but didn't have any duplicate y coordinates, right? And then as a result, our inverse function has a restricted range as well, right? Now, does that mean that this is the only angle measure that has a sine value of 1/2? Definitely not, right? So if we look at this problem, if we ask to solve for x, well, the natural first thing to do would try to cancel the sine off, right? What would we need to do to cancel out this sine in front of the x? We'll apply sine inverse to both sides. Then what? What should our answer here be? Is that the only answer? No. Why is that not the only answer? Okay, why would 5 pi over 6 also be an answer, though? Maya? If I take the sine of 5 pi over 6, do I get 1/2? Yes, right? So that should be an answer. Can we get that answer from our calculator? No. The calculator would never give us that answer, but we have to know that it's out there. Are these the only two answers? Nope, there's lots more. For example, that's an answer. And that's an answer. And that's an answer. And that's an answer. What's going on here? What was that? Yeah, so what's the relationship between these angles? We have a term for this. Starts with a C. Call them coterminal angles. Remember that? So how many answers do we really have to this problem? Infinitely many. Why is there infinitely many? I can keep adding 2 pi. Can I only add 2 pi? No. What else could I do? I could subtract 2 pi as well, right? So one of the important things we're going to have to keep in mind for these solving problems is over what values of x do we really want a solution? Do we want all the possible solutions? Do I just want the ones that fall inside of the unit circle? Do I want some other set of answers? That's all going to be kind of on the table for this. Now, if my answers that I'm looking for are the ones on the unit circle, just between 0 and 2 pi, then yes, the first 2 answers we listed was all we needed, right? If, say, I wanted my answers between 0 and 4 pi, then those 4 would have been the answers that I needed. If I wanted my answers between 0 and 6 pi, then those first 6 of them would be the answers that I needed. And you guys can see that we could do similar things in describing different ranges of values that we'd want our answers in. You just have to continue finding angles that are coterminal to the 2 from our unit circle until you've filled up, found all the answers in that given range of values. So you're just going to be looking at things coterminal. Let's do some more examples of solving. So let's say that we want to solve for x the equation cosine squared of x is equal to 1. And we want our answers from 0 to 2 pi, basically just from the unit circle. So what would be the first thing I would want to do to solve cosine squared x is equal to 1? What do we think the first thing we should do here to solve this is? Maya? Yeah, good. Square root both sides to get rid of the squared. Now, when we square root both sides, what's going to happen? Yeah, I get a plus or minus. And obviously, the square root of 1 is just 1. So really what I end up with is 2 separate equations here. Everybody okay with that? So to solve each of these, we'll just take the cosine inverse of both sides. And then what? I go to the unit circle. Specifically, what am I looking for cosine inverse of 1? The place where the x-coordinate is 1. Everybody agree with that? That happens at exactly one location at 0 radians. There's not a second value where that happens. How about for cosine inverse of -1? What would the value there be, or values? You're looking at a y-coordinate if you said 3 pi over 2. Cosine is the x-coordinate. So just 2 locations. Everybody agree with that? Let's look at a different example. Oops, I wrote down the wrong thing here. Hold on a second. So let's say we want to solve 3 tan squared x is equal to 1. For all values of x. Now, is it going to be possible to write down all the values of x here? To list them? No. Why not? Yeah, there's infinitely many. So what are we going to do instead? We're going to describe the pattern of kind of how to find them, and that'll do. Okay? But let's first solve this for x. What's the first thing I'd want to do to solve this for x? I wouldn't square root yet. I'd divide by 3 first. I mean, you could square root first, but it gets a little messy if you wanted to do that. I said square root, started writing it. Everybody happy there? Now, square rooting both sides seems a little bit more appropriate. So there's that. How do you square root a fraction? Anybody remember? No. No flipping. Pull that. Good. So you just square root the top and you square root the bottom, right? The square root of 1 is just 1. And then the bottom is the square root of 3. What's the other way that we might represent 1 over the square root of 3? Yeah, square root of 3 over 3, where we just rationalize the denominators there. Now, because of the plus or minus, we'll split this up into 2 equations. And we will be taking the tan inverse of both sides. And now what? I go to the unit circle. Now, what am I looking for on the unit circle? Yeah, I'm looking for y over x. So, where am I looking for? So if I say I notice that that's a location on my unit circle, that works, right? Everybody see that? That was at specifically pi over 6. I also get that same thing happening at 7 pi over 6. And then over here I have that same thing happening at 5 pi over 6. And also at 11 pi over 6. Ben? Well, you knew there had to be a square root of 3 in it. And there's only a couple of values on the unit circle with the square root of 3 in the x and y coordinate. So it was going to be either where y is 1/2 and x is square root of 3 over 2, or it would be the other one where x is square root of 3 over 2 and y is 1/2. So you really have only like it's a 50-50 shot, and then you just can check it. So there's not, I don't know, does that satisfy you though?
Yeah, I was wondering why you put that one and how do we know it?
Oh, I was looking for something with a square root of 3 in it. And you can see looking at there's only, the square root of 3 only, it doesn't happen that much, right? It's either going to be, give you 1 over the square root of 3 or square root of 3, and we don't want the square root of 3. Okay. So these are my unit circle values, right? But we want all the answers. So how would I write that? So this is our answers for the x's on the unit circle. How would I change this to represent all the x's? Okay, so Allison says, can we add plus or minus 2 pi? I'm going to do you one better. So how would I write all the angles coterminal to, say, pi over 6? How would I find those in general? If I wanted all the angles coterminal to, say, pi over 6. Leonie? I'm sorry, what did you say? And when you say multiply, you really mean add. Yeah. So we're going to do 2 pi times. So you have 2 pi, 4 pi, 6 pi, etc. Notice that those are all whole number multiples of pi, right? So I'm going to say we're going to add 2 pi times k, where k is. What kind of number does k need to be? Doesn't need to be even. What kind of number does k need to be? What? So the whole numbers don't include negatives. Could k be negative? right? Because we can subtract 2 pi as well. So what do we call those numbers that are whole numbers that are positive and negative? Starts with an I, integers. So the symbol we use for that is there. And now I can do the same thing. It's an integer, right? That's what we said right after it. So take a look at these answers here. There's actually a more compact way to write this. Specifically, look at these two answers, pi over 6 and 7 pi over 6. Did you notice anything there? How far apart are those two answers? What? Pi over 6 and 7 pi over 6 are 2 pi apart? Just pi, right? So if I then compared 7 pi over 6 with the next coterminal angle, which would be, or the next coterminal angle to pi over 6, how far apart are those going to be? Pi again, right? So I could condense this down to just one answer. Now instead of finding everything coterminal to pi over 6, I'm acknowledging that those two answers, pi over 6 and 7 pi over 6, are pi apart. If I go another pi, I'm going to get to the one coterminal to the other one. Do you suppose this happens very often? What we're doing right here? What do you guys think? No. Do you suppose it's predictable when this is going to happen? Yeah. Anybody want to venture a guess as to knowing when this is going to happen? When your two answers can condense down into really just one answer? In the looking for, solutions over the entire real line, like we are here. I could tell right away at the start of the problem. So let me give you a hint. Remember that for sine, sine is positive here, and then negative there, right? So if I have two positive answers or two negative answers for sine, are they ever going to be pi units apart? No, right? It's impossible. Now for cosine, remember cosine is positive here and negative here. Is it ever possible for the two answers, or two positive answers or two negative answers for cosine, to be pi units apart? No, right? Because the quadrants are right next to each other. Tangent is positive here and positive here, and then negative here and negative here. Maybe I should draw those kind of like an X. Is it possible for the two positive answers, the two negative answers there to be pi units apart? Yeah. And in fact, they'll always be pi units apart like that. So whenever I'm dealing with a tangent function that I'm solving, I know that this sort of thing can happen, and likely would happen. Is that okay? Let's do one more solving problem. So let's say we want to solve 2 cosine squared x plus cosine x is equal to 1. What's the first thing I'd want to do to solve this? Maya? And what's that going to do for what? Okay. I mean, you could, but what are we going to do after that? Well, if you took out a cosine, yeah, I wouldn't. Dividing by 2 is not really going to be helpful at that point. I mean, again, so then you'd have cosine squared x plus cosine over 2 equals a half. That doesn't seem like that's really where we want to be going either. Let's look at it this way then. If I take the cosines out of there and just replace them with a generic variable. How would I solve this equation? Huh? No, let's not. This is Algebra 3-4 stuff, guys. We spent like, I don't know, 3 months probably solving equations that looked like this or similar. Really not different than factoring out the cosine, right? Ah, there we go. So James says, why don't we subtract 1 from both sides and then try to factor this? That's what we're talking about. What's the other option if this was not factorable? It is, and that's what we're going to do. What would the other thing you could do if it did factor? Ugh. Really? If this doesn't factor, what else could you do to solve it? Quadratic formula. You can always use the quadratic formula. All right. All right. So we're going to factor this. To factor this, what do we need to be? What do we do? You need to find 2 numbers that multiply to give you a times c, and then add to give you b. What's the value for a here? 2. What's the value for c? -1. What's the value for b? 1. What are the 2 numbers that multiply to give me -2 and add to give me +1? positive 2 and negative 1, right? Everybody agree with that? So, what do we do with this then? We take our 2y squared plus y minus 1 is equal to 0, and we split up the 2y into, or split up the y into 2y plus a negative 1y, and we still have the minus 1 equal to 0. Then we're going to make two groups. When we make our two groups, what's the thing that we have to remember? Have to have a plus sign in the middle of our two groups. If it's a subtraction symbol, it's fine. You just write it as plus and negative, like I've done here. Fixes it, no problemo. From the first group, we should take a greatest common factor of 2y. Okay. And what's that leave us with after we factor out the 2y? Y plus 1. From the second group, we can take out a greatest common factor of negative 1. That leaves me with y plus 1. Do you see a greatest common factor now? So if I look at this and this, what's the greatest common factor? Y plus 1. And what's that leave me left over after I factor that out? 2y minus 1, right? So now we've got it factored. What's the next step into solving this? Good. So I take each of these two pieces and set them equal to 0. So I get y equals negative 1 and y equals 1/2. Right? And now I'm done. Right? What are we trying to solve for? Cosine's an operation. That'd be like trying to solve for plus sign. We're trying to solve for x, right? So what does y equal again? It's equal to cosine x. So let's go ahead and make that substitution back in. So to solve for x, we can do the cosine inverse of both sides. And what's the solution for cosine inverse of 1? That's 0. And the cosine inverse of 1/2. Oh, thank you. So that's pi then. How about cosine inverse of 1/2? The two values there are pi over 3 and 5 pi over 3. Did I specify a range of values that we wanted this on? Oh, we need to do that then. Let's get crazy here. Let's say we're going to go from negative pi to pi over 4. That's a weird interval, but that's fine. All right. So these answers are definitely on my interval, right? Everybody agree with that? Yes? Okay. If I add 2 pi to this, is that on my interval? Remember, this is the interval that we're working with here. That should be on there, right? So I'll write that down on my list. Okay? If I subtract 2 pi from this, well, I guess I should do this first. If I add another 2 pi, am I on that interval? No, right? 5 pi is too big. Everybody agree? So we've got all the positive directions. Now let's look at the negatives. If I subtract 2 pi from this, am I on the interval? Just barely, right? Because I have the bracket. The bracket means it is including that value. The parenthesis does not include that value. So we are good there. Now we have to do the same thing for each of these. If I add 2 pi to these, are those on the interval? Yes, right? So that's going to be 7 pi over 6, and then 11 pi over 6. Or I'm sorry, I don't know why I said 6. They're over 3. Everybody's okay there? Maya? Well, I haven't done the subtractings yet. Because I know that I get some negative answer, so I have to look at the coterminal angles that are negative or less than. So I have to both add, I'm checking adding and then subtracting. I just chose to check the adding first. Is that okay there? If I add 2 pi again, are those going to give me answers? No, because right away we can see that this is 4 pi. That's too big already. So don't have to worry about that. Let's subtract 2 pi now. When I do that, I get negative pi over 3. Is that in the range? Too small. Negative 5 pi over 3 is smaller than negative 1 pi, right? Too small. If I subtract 2 pi here, I get negative pi over 3. That one's okay, though, right? Everybody agree with that? And obviously, if I subtract 2 pi again from that one, it's definitely too small, right? Because I'm subtracting 2 pi from a negative, so it'll be way too small. So this is my list. Everybody okay with that? So again, I just checked my answers, looking for coterminal things in either direction on this one, because I could have negative or positive answers, and just found the next coterminal thing and checked to see if it was in the range. Everybody okay with that idea? All right, I'm stopping here.